Okay, guys. Let me dial it back, Billy. So we're going to go ahead and hit Rolls Royce. We're going to hit the some carbon fiber stuff. And
National Composite Center is manufacturing.
And I'm going, you know, the technology is not there yet. All right, no matter what great machinery they have, it's still not the greatest machinery yet to make the to withstand the stresses of the PSI of where the Titanic was. It's not there yet. Here's a fancy. They've got all types of fancy machines. This is 3M. There's quite a few of them. Now, I reached out to my man at the I've got a few actually, subsea guys. This is what the carbon fiber looks like, the tow machinery. So the tow preg, see it? CMC is compatible with existing automatic systems. So, and how you wrap it, etc. Now, it's just not there yet. No matter how fancy these machines look, they're not there yet to get the quality you need, plus the PSI you would need to because it's going to go in compression, and the carbon fiber along with the epoxy can't take that deflection, that deformation. Thinking is if you make it larger and thicker and thicker and thicker, it's now going to overcome the lower PSI and have to make it through all the layers of it to be able to push that one layer at the bottom here. For example, there's the carbon fiber here. To be able to push that one layer down here, if you push on the top, remember I showed you that with that with the models that they would tape, etc. Well, that's the thinking, except for this is too great of a pressure. It's still squeezing the tube up to in the tributary area, which stresses the critical shear zones where it's connected to the end caps. And we have the extra weight, the weight on the end. A lot of people think that you can just because it's underwater, it's puts the pressure on the door on the end caps that keep it sealed. Well, it's like being in a car going down in the water that you went over a bridge and you landed in the water. You can't open the door even when your car is. Let's say this is the bottom of the bottom right here. All right, so let's do this. Here's your bottom of your vessel, and the bottom of the water. Here's your car. Okay, here's your car, and I'll give you some tires like that. Okay, and you've got this funky car. And here's the PSI. Let's just say this is you still have here. I'm just going to give you 33 feet to go. All right, 33 more feet to go. Right here, your car is fully flooded. So this is fully flooded. All right, fully flooded. FF. All right, just to do that. Fully flooded right now. Your car is, and it's been fully flooded since. Trying to do delete, and I'm pressing the wrong keys. Yeah. It's been fully flooded now for the past 100 feet. This is a 133 foot deep section that you happen to find when the war on the Darwin on. So you've now been 100 feet and you've been fully flooded up here at 60 feet. All right. So for the past, for the past 36 feet, 60 feet, I said? Well, whatever. Let's change it to 60. You've been fully flooded since 60. For the past 40 feet, you've been flooded. And you're trying to open your door for these 40 feet, right? 40 feet. You've been trying to open this door, and you can't figure out why. You got water fully inside here, fully flooded car, but you can't open it. Well, as you go down, the pressure outside of the vessel is also increasing, and the water inside is not at that equilibrium of the pressure outside yet. So this is why, even though your car is fully flooded, you can't open it. So no matter where the sub is, once it goes below the water and it starts lowering itself, it can't open because the pressure outside is not equal to inside. All right, it's just not going to open. So just keep that in mind with theory. Now, when this car gets down to the bottom and the pressure at the bottom equalizes, you can open this door, pushing against the water with your door, the door weight, etc. So it can open it at that point. You can open it there. Let's delete this. So you've got this tractor trailer now. All right, so you've got a tractor trailer, and it's connected here, and you go over the bridge. This compartment in this one's what, much heavier than this one, isn't it? If you guys don't know that, you drop a heavier ball in the ground, it's going to go down heavier. Now this is buoyancy stuff we're talking about now, and that's a deep dive, right? It's a deep dive on buoyancy. That's why they put that one piece on the tail end. But you've got, is it in the right place for making the buoyancy of this vessel? 2/3 up, let's say, or is it with that? Is it half? Is it just below the water surface? How much stress is this creating in torque action here? Okay, watch this. Keep track of this. This will be a short video. Yeah, you guys like my long goodbye, so I'm giving you a short long goodbye. So I'm going to end this video soon. All right, that's a shout out to my people that love my long goodbyes. I guess I got to bring them back because I got some negative feedback for not doing my long goodbyes. All right, so this is connected here at the back of the car or vessel, right? You want to think of that now. So I just wanted to add this part so you'll know that what I'm trying to explain to you. As you go deeper in the ocean, the fluid pressure increases, the PSI increases. So your buoyancy actually goes up. It becomes more, the same vessel is not going to behave the same as it would at the lower levels. So he might require more weight to stay down the bottom, or thrusters even to stay at the bottom as opposed to at the top. So at what point did he no longer become buoyant going up? What was the anti-buoyancy? It wasn't the PSI. That would actually help push him up. Why did he not rise? What was the failure here? Apparently, with all the history of the carbon fiber cracking and etc., along with the failure at the ring and the model, showing the failure at the model, the ring failure, the interface ring. Apparently, that came to that check was cashed. It's connected there with that titanium ring. But we see it float all the time. So we're like, oh no, it works. It's okay. This system works. As you see it bobbing in the water, obviously it works. But in reality, you've got your buoyancy down here on one end. On one end, you have all your buoyancy down here. And you've got an air tube in here once you put the air in it. So there's a little bit there. How much of this is creating a torque like that? Okay, we can leave it like that with the vessel. How much of it is really creating a torque like that? We saw them test this alone going down on the skid, but it was strapped down. We didn't see it unstrapped without the backpack on it, without the rear on it, right? We didn't see what that looks like without. What was its neutral buoyancy? How did it behave? Was it truly like that, like a dive, or was it like like this? Was it flat, like a beautiful, and just sticks out of the water just by a little bit, or something like that? There will be some torque in there because they had weight in the front. They had oxygen tanks in the front. Oxygen tanks in the front of this nose. That's kind of counteracting the back up here. I don't know what the weight of them was. They recovered them. I guess it still was in design. So I don't know what that weight is. But I do know that who helped with his buoyancy, per his own words, is the electrician. That he considered himself one of the buoyancy people in here. Now, I'll give him some, maybe he wrote the wrong word on buoyancy. Maybe he didn't, but I have not released it yet. It's in a private room. He states that he helped with the buoyancy. So you've got an electrician that Rush hired. How many times did he work on a sub? He had tons of experience on subs. He actually did the help with 30 subs. Oh, I meant 3. I mess my numbers up sometimes. I meant 3 subs. I'm just kidding. He worked on no subs before. He had no subsea subs that he worked on submersibles before ever. In fact, he was he was like Tool Time. He worked on cell phones but printers also. So printers and cell phones. And of all things, he didn't do it 1 year, 2 years. It seemed like it was really his passion. He had 16 years, I think it's 16 years and 1 month doing that. Apparently before transitioning to deciding that he can do subs. His own words were when he was trying to be recruited, his own words paraphrasing, that they try to recruit me, a recruiter tried to recruit him. He said, no, I don't want to work on military stuff. And he said, no, the recruiter says not military. And he's like, oh, well, what is it then? So he went from, no, I don't want to work on subs, no interest, because it was military based, to, oh, it's private? Oh, yeah, I'm on board. I can learn fast. And just think of this recruiter. This recruiter could have hired many experienced subsea people to do this. But this recruiter went to a guy that does cell phones, 16 years of them. He didn't have a passion. He didn't really reveal to us, oh, and on the side, I just had this crazy passion for buoyancy and subsea stuff. I would volunteer and I would just do that. No, none of that's in the history there. No. He states that it's his first time. So did he nail it? Did he nail everything on there? Is he responsible for some of that electrical stuff that we talk about where it goes down backwards and twisty and tossy? Well, it would seem like that would be under his purview to say, hey, I need you to do these testing systems before you dive each time. Now, he wasn't there at the time of this incident, but he said he was still subcontract to be called in when they needed him, including over the phone, as I understand, So who they had taking these the fans off. I'm going to call them the fans. The thrusters. Who was doing this rewiring? Just 1 minute it was working, and then between 1 minute working, the last time it worked, to when they did whatever inspections and removal or R&R, remove and replace stuff they did, that they managed to get the wiring all messed up. How is that possible? I mean, didn't this guy number stuff? I've got heavy equipment I like to work on, hydraulics guides. I'm kind of a freak for hydraulics. Do you know hydraulic equipment has little tags? I could show you. It'll be green, and then on the other end of the line, there'll be the other end of that line, which can go heavy, there'll be no other green wire tie. So you go look in there and you see this green wire tie, go right back. You know where it belongs. That belongs in the manifold right here. This, no matter what path it takes, this is the end. They wire tie them first, and then they feed them. There is no mistake. Or you wire tie one end, run the other length, and as you're making that connection, you know it gets the green wire tie, you wire tie it. Green. It's color coded, it's matched, you cannot make the mistake. And then the only way to do it is, of course, you pull your hydraulics out and put it in and screw it into a different port. But that's only doing testing do you do something like that. And he was what? He was known to swap, right? Let's swap the domes. And that tells you that they might have been redundant. If you could swap them, that means they're redundant. I know one of my subsea guys said he doesn't think they're redundant. And maybe he's right, but I think they're redundant because he said, based on what he stated, he's going to swap to see if it now works. So it seems like it's redundant, although I will share with you guys, I'm dealing with quite a few subsea engineers that write me, and a few of them it's quite a few different opinions I'm getting and thoughts, but they're none of them are saying, this was awesome, this thing should have worked. They're all saying, maybe this is okay, but no. And they'll send me images of what looks like what's okay. For example, wire ties. Totally acceptable in the industry to use wire ties. All right, wire ties are all over the vessels. Totally acceptable to wire tie them and with that deflection. So we're looking at buoyancy. So let's use this part as the car tractor trailer idea. If these go in the water together, are they going to have the same buoyancy? They're not. And so this is going to want to torque down, right? It's going to want to go down further, pulling from here. This is where I get this pulling effect. And instead of here, if the audio scripts are correct, hearing noises at the aft, that would explain it. Also, that darn hinge. Remember my hinge, my favorite hinge. They keep trying to resolve torque with this little baby hinge they put up front there. And then when it gets in the water, this may work. But outside the water, no, you're getting stressed. And again, what do they use for securement here? They do have a strap across the back that goes to the interface ring. Still puts the stress back on the interface ring, which connects to the carbon fiber. For one of the viewers, she asked me to be more clear about a couple of things. One of them was a flange. Okay, a flange is, wow, flanges are everywhere. Like if you have a muffler and here's your muffler, and if they don't use an expansion and try to sleeve it in, sometimes they'll just be there'll be this part is the flange, all right, this part here. And this is what you can bolt to, the flange. You can bolt here and here, pulling together, and it pulls these two together in whatever. It could be flat, it could be tapered, it could be however the designer likes. That's a flange. That's your flange. Flange on flange connection. It can be through bolted or screws. There's going to be a nut back here and a bolt over here, and you pull it tight. That's the way they're doing it on this vessel, the flange system. And then part of that flange system, though, it is the interface ring. Interface ring, and I want to keep with the drawing as opposed to confusing people with. I'm going to keep with the drawing right now. So here's the tube, right? The vessel. Well, yeah, we'll do that. Okay. So there's a interface ring. I'm making it larger. All right, and thought I could flip it, but I can't. All right, that works for me. So I just showed you this flange up here. This is this extension right here. These little parts that kick out. In here are holes, and you can run a bolt through it. And this part right here of the vessel, I'm oversizing it on purpose so it doesn't blend. But in reality, it's equal with it goes across the carbon fiber. Noteworthy is it only goes across the carbon fiber on the outside tapered. It is not tapered on the inside. In the inside, let me make it clear, it doesn't present as tapered in the inside. Now we've heard everything from 667 layers, 800 layers, 666 layers. I've heard quite a few layers, but I think he might be counting that one that we mistakenly thought he was making a carbon fiber out of, wrapping it. That black one they showed that they keep wrapping. That's not it. That just, I refuse to accept that that's it. That cannot be it. It's got to be the technology that he talked about that I found that one video. Yeah, I published it. And it uses that fancy head machine, looks like this. All right, so the flange, so here's and then you have a door. Your door is that dome. They had to put a flange on it to be able to bolt it together right there. And here's the dome. I'm going to cut it short a bit. There's your dome, and I'll size it down like that. And they close the door and they bolt it up together. How's the seal done? Not just at the bolts, but it's probably interference fit. That means it's say this is in thousandths of an inch. So this opening might be right here, might be tapered just a hair. And when I say hair, it might be 0.003 of an inch. And then this one's tapered on 0.003 of an inch on a taper. Might be 0.005 of an inch. So it's a 2,000 of an inch difference. So it could be 0.002 of an inch. And when you close this door and seal it, they do a temporary vacuum. Now, I thought about that vacuum, and I was like, yeah, that makes sense now. And I thought about it, because I have a vacuum machine too, and I was like, but you got people in here. You can't pull a vacuum while people in there. You're going to kill them. But yeah, you don't need to pull the vacuum like I'm originally thinking. You just need to see it go down, that it can start sucking, going negative. So the negative would be, like 30 is a great vacuum, a vacuum of magic. So you just start pulling it, and you start seeing the vacuum go to 1. You stop. As soon as it goes to 1, it doesn't even have to go anymore. You stop the vacuum. In fact, for safety reasons, you'd probably have it so the thing can't pull a vacuum P out in 1. It would just shut off. The point being, if there was an opening here at this door, it could never pull a vacuum. It's like you trying to suck in all the air out here. You can't do it. So as soon as you started seeing pulling a vacuum, 1, 2, that would lower your atmospheric pressure in there just a little bit, but the person could still breathe, and then you would automatically shut it off. So you don't want to kill them. And so it'd have to have an auto shut off on it. I just couldn't see you manually doing that. But with this guy, I can see him manually doing it. Just pull a vacuum, then unplug it when you get to so far. You know, you'd have. I think one of the safety features would be have a DC type vacuum tool that you turn it on, and it's DC powered, and it just dies as it. So even if the worker fell over with a heart attack or got swashed off, the machine isn't running and depending on an independent person to start it. A rogue wave comes, and then you decompression everybody in there, which would be terrible. So you would have it so it's on a battery, and it can only work so long, just 1 minute, and then the battery dies. That's it. It's like done. Pump screwed up. Okay, but they do have a port they connect this to. That's a concern to me also. The port they connect the vacuum to, how are they sealing it? How are they? Because they got to be able to pull a temporary vacuum. How are they doing that? Where is that connection? That's one of the details. Hopefully, the Coast Guard can figure out. It's his statement that they pull a temporary vacuum to confirm that the door is sealed properly. They don't want to go down so far and water starts gushing in. This becomes a gushing in. They don't have the diver there to close it. The pressure coming in doesn't allow the door to reseal, if you will. It's too late. It's like having your window partially rolled down, coming back to the car. And then you're like, oh, let me try to roll it up. Well, you don't have the ability to close this door. It's 3,000 plus pounds, no handle there. You don't have that chance of grab the door, grab the glass, close the door. No, you don't have that ability. So you'd have to trust the guy bolts it, then do the temporary vacuum, quick vacuum, and now the door is sealed. And the back, you don't have to worry about, that's always sealed. Theoretically, always sealed. So pre-dive, they pull a vacuum. What does this tell you? Well, pre-dive before this last dive, that means if they pull the vacuum, that means the seal was not broke yet. Because it would have found, theoretically, it could find the if there was a break between the real hull and the glue out to air, out to the oxygen level out here. You have these oxygen bottles down here. As the electrician stated, he made it very clear these are oxygen bottles. It's not a mixed air. He states it's oxygen. Oxygen is very explosive. You light your acetylene first before you light your oxygen when you're using a torch. Oxygen is the one that will end your ass. Acetylene, it's good to go. But this oxygen bottle, that's still a question to me about how was that rigged up. And, could it be a problem at one point and be part of the destruction of the vessel? I've had people tell me that, it could be a suicide by one of the players in there. You can't eliminate that. You really can't. Oxygen-rich environment doesn't take nothing but a match, right? I guess nothing but a match. Now, with that said, there is a scrubber in here. I don't know the oxygen content in there. I didn't see a screen for that says here's our oxygen monitoring system, and it's at the level where you couldn't you can light a match here, right? That's it. But you could light a match in there, perhaps. Maybe the oxygen content in there is similar to the oxygen content that would be as you and I see it in up here in space and not down in this tube. In other words, that he's maintaining, even with pure oxygen, he's maintaining an oxygen level that's equivalent to our saturation we have up here. That it's not different. It's not a different saturation of our blood gases, it's called. But if it is oxygen, fuck. You're in you're riding in an explosive vessel. All right, so let's. I just don't see that. I don't see that. Nobody talked about having to be treated differently when they come out of there. So I just don't see that. I think that their scrubber, their weak scrubber back here is soda sorb. Yeah, I get it mixed up sometimes. But somebody will correct me in the comments. was probably neutralizing that. But remember, this is a steel rib down here. So now we go to my steel rib. Now I get rid of this for a moment. Okay. So now's the time to say I'm going to end this video because I just want to leave you with this. And then now's the time I continue the video. So down at the bottom of here, I showed you that this is and I'm extending this out. It's a rib. All right. And he had, I think, dual tanks. I think I recall seeing one opposing tanks here and here. Now these tanks are not for free. They are heavy as all get out, okay? I don't curse. I would say fuck, but they are heavy as fuck. But I don't curse. So I think he has dual tanks, and then some other things. The plumbing back to here. Back into feeding the outside rib. Remember, this thing is ribbed. It holds another liner here. And I think this liner might be something like this liner. Oh, all the times it didn't deform this time? Yeah, it's not going to work. I'm trying to... Oh, you know what? I can do this. And hopefully it fixes the shape. Nope, but good enough for me. So that liner might go here like that. Well, that's interesting. That's interesting. The thought process on that. Really? You suck. Hold on. Oh, and then you're going to keep that shape. All right, I give up. You're going to hell in here. All right, there's your damn liner. There's the gap right here. Now that gap's against this, is controlled there, but down the bottom, it might be sitting on top of this floor. Which means they created this rib right here. This is the profile now that would be a new critical shear zone. That stress that I talk about, where it's not a tributary area only, that you have down the entire length of the vessel, where the ribs are coming in contact with the outside of the vessel because it's not magically floating. So this is the length of the vessel. You have this dissection. There's that gap right here. I'm going to change this color, I hope. And this is where the people would stay. And let's change that color to that one. So this is where the people would stay, and the rear dome is here. So this is where they all cuddle up, whatever which way. Look out, lean down here, sit on the shitter, look out the window. Okay. No, that's interface ring. That's up here with the window. So there's this. That's the shitter there, the toilet. All right, so there's the interface ring, much larger than it should be. It would be way down, scale way down. Put the shitter back here. Oops. Okay. So to get the best room in the house, you always just got to pretend like you got to take a douche. And you get the best room in the house. Okay, so Captain Nemo's back here, right? That's where he stays by his station. So over here, though, again, this is, when it squeezes, it can't squeeze this because these tanks and all, nobody's talked about if you're squeezing this. Nobody's talked about, wow, my ass raises up. When they squeeze this, we get closer to the ceiling. Squeezing this tube, right? If you squeeze the tube, you see how what happened to the bottles now? I'm right around the bottles. I'm exaggerating the squeeze, but nevertheless, it needs to squeeze uniformly for a circle, for the load equally around there. You can't have it not squeezing uniformly. Back to buoyancy. So the buoyancy on the rear of the vessel, was it tested by itself? Just grabbing the rear, dunking it in the water, and that buoyancy. Or did they treat it as one once it's clamped together? Did they then start adding buoyancy? Remember, they changed it from white to yellow. They played around with it. In doing so, they try to treat this as one single unit with the air in there. And I don't know what weight they put in there to when they balance this. Clearly, the people weighing different matters in such a small vessel. Where they're located in here changes the buoyancy, the center of gravity for the buoyancy. The axis, right? So of the vessel. So do they have, did they do the math for that with the people in there? All right, with them huddled up the front, huddled up the back. How much of this would want to go have a negative effect as they're going down, going at wants to lower itself at a different rate? So the car by itself, right, wants to lower itself at one rate. But the tractor trailer back here wants to lower itself at a faster rate. It's just more solid. It's more solid and it displaces, to get to a point where it's no longer displacing water more than what it weighs. It needs to get down there deep. It then starts finding its neutral buoyancy. And how would you know that? If we could only find the descent records, we would see that, right around 10,000 feet maybe, if I get this right around 10,000 feet, they would start using thrusters maybe. I theorized that they didn't just use weight to get to the bottom. That at some point this vessel, with the people in it, different time, different people, different weights, different location of the people in the vessel, that they had to, like a cargo master, you have to balance this out, that they had to use thrusters to start taking them down, to get lower, because at some point the PSI, so I found the chart, I found a better chart, and it basically shows at 1,000 to 6,000 feet, it's still increasing in pressure. We're talking, hold on, I found it on my phone, you bear with me. So I'll just take this as an animation. Wish I could give you a cat animation. Hey, how you doing? Yes. I have a treat for you, Stevie. What would you like, some tuna? Come on. Come on, Stevie. Come on. He jumped right on it. He's getting his pill tonight. Oh, he jumped on it. There's our buddy Stevie. Little white paws, little white socks. Hey, Stevie. See, if I make noise like that, the other cats might run off. That's why I say it's okay, Stevie. Right, Stevie? We'll keep these other cats away, right, Stevie? All right. So up to 1,000 at zero top of water, right? The pressure is 1.02813. So what this chart shows is that your density, that it does increase with depth. As you can pause the screen and read it, you can look it up under yourself. I think I found this one under Britannica. It's not. It seems like a better one than the other one I had that I was able to locate. But I like this one better. It's a little more accurate. But it shows you it does matter. The density increases per depth. Your salt compression, etc. And they give you a little thing about sea level water rise. If you if it wasn't compressible, what would the difference be? So you see, water compressible did Pascal get it right about fluids are incompressible? Well, he got it wrong. Fluids are compressible, especially your oxygenated blood is compressible. And you could probably argue back, well, then that's not the fluid. Well, it is a fluid, and so is the seawater. So he didn't have access to purifying, getting out all the oxygen out of his water when he did his sample, his water. He showed it to me. I remember I was over there, and he's like, "Hey, check this out, Kai." And he boiled some water because he wanted to look clean. He had well water. It was nasty. I remember it. Remember it like it was yesterday. And so I said, "What are you doing, dude?" And so he's like, "Hey, check this out." And he made that little tube thing up, and he pressed it down. He's like, "Check it out, man. I'm publishing this shit. Water's incompressible." I'm like, "Wow, that's pretty cool." And I left, and I was like, "Man," I said, "Pascal, he's brilliant. He's brilliant." And then fast forward a few years later, he died. I still stuck around. And I discovered that the fluids are compressible. So why do they teach that fluids are incompressible? Why do they just teach it blanketly? Why not just teach the truth? Just say that fluids are compressible. For the most part, they may not be compressible, but they are compressible depending on the viscosity, your contamination in the fluid, etc. But fluids are compressible. They will transfer the load, though. They do have ability to transfer the load. But to just say they're incompressible is incomprehensible to me. That's a density, rather. At 1,000 feet, the density goes from, so we're going from, just remember the last, it's all 1 in front of that. So first we have 0.028, 13. At 1,000 feet, we have 0.03285. And then at 2,000 feet, we add 0.03747, which is about an entire, so the top one at sea level is 0.02813. Now 2,000 feet down, we're at 0.03747. We've almost gained a point. We gained a point, but it's almost around the clock. We're missing like 50 more points to make it even in the 1,000 scale. 1,000 scale, the 10,000 scale. At 4,000 feet, we're at 0.04640. It's a huge difference between the top level being up here at the top and down there 4,000 feet. So at some point, the density of the water increases. And remember, to be buoyant, it has to displace more water than what it weighs. So up here, it's got to displace more water than what it weighs, but it drops faster. But around 4,000 feet, it's going to start slowing up because the water's more dense on the surface. It's now going to be able to displace with the same surface. It's now going to slow up because it's displacing closer to it's getting value. The density of the water is getting tighter, so it's able to slow down. At 6,000 feet, it's now 0.10 correction. So it'd be 1 again in front. Remember, so 6,000 feet, we're at 0.5495. That's the density. So 6,000 feet, we're going to slow it down again. At 8,000 feet, we're going to slow it down again. At 10,000 feet, it's going to slow down again. So if you could imagine this, let me just type this here. So let's see. Let me just give you a visual. So let's do. Here's the bottom. So here's my text. Okay. Let me show you. This will be 10K. So this is 10K, 1,000 feet, right? This is 10K feet. And this is per the chart I have. Why did they put that way? Yeah. Oh well. So it's 10,000 feet. We're at 1.0. I'm going to do all of them. 014. Okay. So that's that. And we'll give it a coloration. Okay, here you are here at 10,000 feet. You're not at the bottom yet, so you're right about here. So this will behave differently here than up here. Now let's give another one up here. Show you right below. Yeah. So let's go with 1,000 feet. So 1,000 feet, I should have said 1K. 1K feet, we're going to be at 1.03285. All right, so now we're displacing differently. The same vessel going down. Here, once the buoyancy is going to be different, however this is set up, than it is down here. And so whatever it is, you have to calculate how is this going to behave, the rear end on your interface ring. This one I'm not worried about yet, breaking it up into sections. This is going to have, this is still going to be, the lid's still going to be closed on this. The door is going to be closed. Your tube's still going to be a tube, but you're going to get some compression on your tube. All right, and remember the interface ring causes that right here. Let me see if I can draw it. Okay. Actually, that might work for me, the sizing and all. So your carbon fiber is in there inside this interface ring. Let's do that smaller. And I'm exaggerating this crushing area here. It's very minimum, but enough to break off the inside lip of that, the inner lip, the upper inner lip of the interface tube. Remember, it looks like that. And the carbon fiber. All this you can help remember yourself. This is what? The bracket. All right. So the carbon fiber's in here. and it's glued. I'm giving you some separation there. It's glued, but deflection here, which is squeezing from the PSI outside, it doesn't quite squeeze in here the same, and if it squeezes out here more, and it pulls itself glue-wise from there. Why not the front as opposed to the back? Well, the back has more weight on it. That's why you have the back more so. So this is that white foam, as you can see, and the density is different than the orange-looking yellow foam. So they did not figure out the neutral buoyancy of this vessel. They were still working on it. As you see in the next image, there's a foam change. And they had another combination of different colors between this one. So it's this is a very significant problem with buoyancy and them not figuring it out. And it could be that they had too much, they couldn't change it, actively could not change it while the different weights were on the vessel. And that can be a nightmare for this vessel as far as once it's in the water, what kind of torque action it creates, these multiple buoyancies back there. I could clearly, if more evidence comes out, I go with the evidence. So if it shows that the front failed first, if more evidence can show that, then I can, without any harm to my feelings, I could switch this around. But if I'm going to pick on something, I'm going to pick on the back because of the weight, because of the tractor trailer back there, and its way it's going to react differently with its buoyancy. However, whatever they put back here, it's not variable. They don't have a way to change the variable buoyancy on this. They can't say, okay, now we're at 10,000, blow ballast tank rear, let that air out and let's just keep the scent going. You guys watch Captain Nemo, right? No. So, there's no way to balance this. Once it's in the water, it's in the water. Now, maybe you could, if you had a computer's monitoring system, I need you guys, you fatty, move forward by 3 inches. Okay, it shows on the scale that we're balanced again. You're good. Stay there, fats. All right. Skinny, come on back here a little bit. Well, okay, good. We're there. Okay, now we're back in our buoyancy's axis is where we need to be without stressing this connection. Or you can say, it doesn't matter. Wherever we put it, whatever we do, whatever stresses on us, it doesn't matter. This glue is superior. It's going to hold up. It's going to hold up under any forces, rotation, torsion, everything. Well, wait a minute. He said there is no torsion down there. So whatever you do, it cannot hold up under torsion because he stated that he did a 0-90 configuration without of the carbon fiber without worry about torque forces. And that might be the death of it. So this glue might have a very weak shear value, and so it would go into shear once you start torquing it. I asked that in that 1 minute video. Pug Face Media was the first to answer, and he gets the shout out that he talked about the shear values. Other people, I say tension value. The tension value would be would create the shear value. So I talked about the tension, how much tension it can take before it fails, and then you get the shearing of it. So what can it take? How much tension can it take? And then was it tested down here? And I would argue that I don't think they did any testing. The manufacturer did any testing with 6,000 PSI on this product. So it matters how that product was tested to determine how they determine the shear value. But they use an electrician to help with this, and and he's used to cell phones and making apps, as he stated, and working on printers. So that's just the death of everything, right? Let's just say that. So let's pick up here on this machinery and let's go from here. All right, I should end this video and make another one. Yeah, of course, guys. I'm giving you back your multiple ending videos. All right. This is temperature monitoring, everything. Oops.
Which is conventionally used to manufacture carbon fiber composites.
Okay. National Composite Institute. So he can't go wrong. All right, so now they have these rollers right here. See the rollers? Got heat. They got infrared right here. They've got this flare device. I know what I'm looking at now. I didn't get to this part of the video, but I've seen this so many times now that I know what these machines, how they lay them out. Even though it's a different manufacturer that I've never seen. All right, so this is the roller. All right, this is the infrared device to help. This puts out the heat, preheat, and a regular heat. And then this is the one that's going to try to find the defects as you go. Let's go with...
We're using AFP for processing CMC materials to provide excellent control over manufacturing parameters such as compaction pressure, layup speed, and layup temperature.
Compaction pressure, he said. Compaction temperature. What the hell did he say? All right.
We've been collaborating closely with our project sponsors,
Look at that thing.
Reaction
Beautiful.
Engines, 3M, Rolls-Royce, and MBDA, to ensure that the UK stays at the forefront of high-temperature materials technology.
All right, there it is. It's laying down nothing, actually. But you see that little stutter, how it came over the top? And that would be a problem. And that's where you get that bunching from that I show you guys. You get bunching and things like that. And so they try to figure this out. But I'm going to show you something right in this image. To the right. What's that? A heat gun. They're trying to figure. This is still a learning curve. This whole learning curve. Terrible use of the words. But it had that little stutter step, and then it creates a problem. So they are down the low tech using each layer, literally each layer, having to visually inspect. And I've yet to find out. So what? When you find that defect, do you align it with a screwdriver? I've yet to find out how do they handle that. Well, I see some shit here, but
completed.
Maybe that warms the glue up on the head, cleaning it off.
It has enabled us to identify a range of key processing variables to ensure that we're manufacturing a high quality.
There we go. So it's white, pre-pegged. All right. So here are the issues here, like that gap that you want it to be touching but not gapped. And then you inspect it for each one of these being layered. Remember I showed you under the microscope what it looks like. Unlike a rope, which is twisted, this is not twisted. Unlike rope, this is not twisted. So everybody say it's like a rope. KMA. Kiss my ass. This is not a rope, all right? This is like this is carbon fiber, and it's more in line with anything, straight line, and I showed you the bands of it. I mean, some of the stuff's amazing.
CMC component.
I watch. So he's going the other direction, heating.
The manufacturing knowledge gained from the project can now be exploited by members of the
Let's see if we can get in closer to that. No, can't, guys. I'm in as close as I can. So now he's going the other way, and then this machine would reset. And there's an infrared right here. Reset, move over.
NCC and benefits the UK's high temperature composites capability.
Oh, that's a one-off.
Following AFP,
So there's your autoclave.
the CMC is placed within an autoclave and exposed to heat and pressure to consolidate the material.
Consolidate, shrink it. Hydraulic door. Hinge.
Processing is then completed after sintering at over 1000 degrees Celsius to enable further densification.
1000 degrees Celsius to get further densification, to get it dense. And visually, she's looking, oh, I got these gloves. And apparently, she gave away what they were really worried about was the inside and outside edge. All right, if you were to look at this, you would see the pattern, how it was laid. In this case, I'm looking for replication. I can't tell. I mean, of course we can see what we can see, but I can't. I still need to get closer. Okay, here's a pattern going this way.
This new automated CMC manufacturing route will enable our customers to produce next generation, high temperature and lightweight composites in a more reproducible and cost effective way than previously possible.
Okay, there's your NCC. National Compositing Center. All right. So, let me get you something else here.
Some challenges when this layout. So there's a lot of advantages, but
Okay, so I've got you here now. So this is what One of my subsea engineers wrote me and sent me this link. Shout out to him. And I said I'd get to it, and I'm getting to it now. So this is what it looked like on the sub. Some of that tearing, if you remember, on the black part. He sent me side by side, so I could grab that image. But and I'm like, yep, I see the bubble. Oh, bubble. Oh, shucks, I'm trying to make a word. Bubblification. I see the bubblification over here. Yeah, I might piss somebody off with that, huh? You can't make up words. Whatever.
Some disadvantages.
You'll never forget where I'm talking about. If I say, you won't forget when I tell you bubblification, will you? What that looks like. I might want to change it to something else. Once I exactly knew what was the cause of it, I'd probably call it something else. Because actually, I don't see it blistering or anything else. So I'd like to reserve a changed name on that one. And let's go.
Down don't always go where exactly you want them to. Whether it be
see that they don't go where you want them to, and this is with the high dollar architectural machine, engineered machine. Now,
because of error in the motion of the robot, wandering of the toes, complex geometry, so on and so forth. There's
wandering of the toes, complex geometry. In the machine.
A lot of variability. There can be a lot of variability on where the placement of the toe actually ends up.
And this is why I'm stating that you're never going to be able to use at this time. This sub would never have worked because it was too complicated, too many layers he was dependent on, and they haven't worked it out yet. They have not worked it out yet. This source is not.
Those defects
is a legitimate source.
Are concerned with overlaps and gaps, but there's also a thing like FOD.
I want to show you FOD, materials to get in there. The clean room, as a couple of people might have stated,
where there's material underneath where you laid up, and it's not supposed to be included into there. There's buckling and other things like that. But my primary concern is.
And the buckling is what I showed you with the tape when I did the reel on the lathe. I showed you that, and there's your buckling.
Overlaps and gaps, and what those are is when the toe of in the course, if one toe is overlapping another, or if there's a gap between the toes as you're laying them up, and those.
And a gap between the toes. Let's see. I think I have an image for you on that one. So this is the toe. Here's a 6K filament toe. Here's a 12K filament toe. I showed you it in a overlapping pattern. Zoomed in, looks like this one right there. And so he's stating that these toes, these filaments, can start overlapping this one and even inside themselves. Or like there, look at that daylight. That they just can't maintain its consistency. I have this open for a reason. Oh, toe fiber. For you guys, textile industry, tow or hards is a coarse meaning rough, is a coarse broken fiber removed during processing, flax, hemp. Anyway, so let's go back over here. Let's get to it. You show what the
types of defects can impart as much as like a 32% reduction in strength, depending on what your application is and what the severity of the defect is. So these kind of defects have to be caught before the material is baked in an autoclave. And
so you've got to catch it but before it's baked in. That means you've got to look at every single layer, 667 of them, every last one, and I still don't know how you're supposed to fix it.
The overlapping gap defects are there for life.
Or defects are there for life.
And so the way they detect for these right now.
Now, I'll give you the heads up. He made these mistakes in here on purpose, he states, to be able to look at them. And just look how hard it is to find. He's telling you what the problem is. There's some twisted toe here. There's some laps and gaps here. Telling you, and look how hard it is to find. They got a magnifier here trying to find it, and you'll see a close-up now of what it looks like in a moment.
Now is completely 100% manual inspection, every single ply. And so
every single ply, manual inspection. You imagine that? So how many people do you get to check what you check? You should have, and how do you do it? Do you put a white marker on it? What do you do? He's got his finger on it now, talking about fog, foreign object. So foreign objects rather. So he just put his finger on it. So what's that do? I mean, how do you fix this? And that they're not stating it. And these are the experts on it at this point that are talking about this. And you know me, I don't like doing a halo effect, so I'm not going to tell you who the experts are. This is revealed in the background. But my engineer assigned to me knows this video content.
You have technicians that go up after each ply with magnifying optics and lights to try to find these gap and overlap defects. And it's a very, it's not a very precise way of measurement, because if you look on the picture on the left, we have a twist and 2 overlaps and a gap in that panel. But it's such a low contrast environment. It has the composite itself has so much texture. Unless you're at the right angle, even from this picture, you can't tell that those defects are actually there.
So what he's saying, at the correct angle is what he means, not like right angle, but unless you're at the correct angle of trying to look for it, you're not going to be able to see it, and you'll see it in a moment.
I know they're there because I put them there, but just from looking at that, you're not going to be able to understand them. And so much time is devoted to this that studies have been done to see what the allocation of cell time is actually done with inspection. And you're looking at about 42% of total cell time used for inspection and data review, and while only 19% of that cell time is actual physical layup. And ideally, you want those 2 numbers reversed, but that's what exists today.
Now, I want you to note that the electrician, the one that was party to this electrical work, spent time talking about the making of the hull. He said it took months. So it appears that maybe they did do this process, that they really did, the months involved that it took to make this, to bake it, to go back, and I don't know about how hopefully the Coast Guard and report that go public will reveal how they did the multiple layers and photographs or any details that they may have released or whether they did not release. Talking about the manufacturer.
And so before I get into the technology,
so this is critical, this image, because this is what I was trying to show to you when the guy was using that squeegee on there. I said, what the hell, is he leveling out the epoxy now in this? And from one layer to the next. But remember, it's spiral. In this guy's example, it's actually lined up. And over here's a line up, and here's a step up. Now, this is exaggeration, but it shows you that you're creating where this is not working. The bond is not there. It's exaggeration in height, but it's still theoretically there. That when you overlap like this, you're going to create this. All right, the ramp up. I talked about that with the tape. I showed you in the video with the tape that I have on the lathe. And I'll put the link below this video of that one. And then I'll show you some tape buckling, things like that. But it turns out they use this high-tech machine that hopefully would then overlap the other direction, and then this direction, and then 45 degrees perhaps. But everything but to stop the double, the inline joint. Here's the infrared machine, preheat lamp, and the roller, pressure, etc.
Developed. I'll say there's a whole bunch of people working on this problem right now. There's systems that are being developed that use laser profilometry, that use vision systems, that use multiple spectral systems, and there's a whole bunch of advantages and disadvantages to all these. This is more what we've developed using infrared.
So let me be clear. This was only a year ago. This video we're looking at is a year old. His ship was built way more than a year ago, to sub. But it was with the same machine that this organization is using.
Just another way to do it. And so this is the technology, the innovation I'm going to be describing today can benefit all these technologies, not just the one that we've developed here at Langley. But what we did...
Okay, there you heard it. Just gave it away. So you guys don't know what he just said. NASA.
Here at Langley, we decided, hey, let's put an infrared camera on the AFP machine. And since every single AFP machine has some sort of preheating element...
You're going to like this next part, and then I'll end the video.
That's heating up the substrate or the material that was already laid down, so that when you lay down new material, it's tacky enough and can consolidate and compact well into the substrate.
All right, compaction. Remember, you got to get it bonding somehow, and it's going to be based on the pre-preg and you want it to marry up just enough where you don't push out the glue that's needed to hold the one string, the one piece of tow string, if you will, to the top piece of tow string, if you will, the filament. You don't want to squeeze it out to the point that there's nothing left. Laying a tile down and you press it all the way out to you put 2 ounces of adhesive on the back of a tile, and you press that flat tile with no grooves on the back. You press that glass tile down the floor onto the surface, so much so that you get 2 ounces of glue coming on the outside. You put 2 ounces on it, and when you scrape off all the outside edges, you got 2 ounces of glue. Or you could say 1.95 ounces of glue left. You defeated the purpose of all that glue. You only used 0.5 ounces. What would it take to do this? It's just the testing is just immense that he would have to do. The 1/3 scale testing, he'd have to destroy so many of them. So many of them. It's just to get the 1/3 to work. Once you got the 1/3 to work to wherever you would just beat it up, take that son of a bitch to 9,000 PSI, and as a joke, it's like, then you've mastered it. And especially if you can master it without manual manipulation where you got to go fix toes. Then you've mastered it. And I think part of the problem is they're giving it a geometry, a shape that it has to work on that the toes can't keep up with. Yeah, you can go round and round a tube pretty easily, but they're also making it go on an angle like this down the tube. And how do you do that? You saw the head. The head is flat. If the tube is curved, all right, then how the hell do you ever go down the other direction without a different head? So, without a different round. All right, so here's your tube. And if your head, this roller right here, you see it flat? If it's... Actually, I could use a damn tube. Hold on. I think there's a shape of a tube. Oh, no, it's another circle. Huh. Okay, that's our tube. Let me make it round. That's the shape of that. And bring it in. Bring it down. Now, how the hell does it fill in there? See the gaps? If you're going that direction lengthwise of this radius, how does it get down there? You'd have to change the heads to match it. And did they do that? Did they change these heads out? I bet not. I bet not. And that would be the length that would help it in that tension, the strong back, if you will, where the sub is like this. This direction here, and here's the head cap, here's the cap, and here's the tail. All right, exaggeration on the tail. That this is where the filament on the back side would work in that long direction. If you could run it down the long direction, it would keep it in tension. But you can see the problem I'm having. You can move this around here, and you still have a problem. You're not going to get, you're not going to, as you rotate the tube, whatever it is. If I could rotate this at the same time, then I'm going to cause buckling of the toe roll. So if I could spin this and roll at the same time, it might layer it in, right? Just layer it in. If you could just figure the right amount of rotation of this, at the same time this is laying it down. But it's always, then it's going to cause buckling in the middle where this is contacting. You're just not going to get it. The only way it would work is you'd have to change this to exactly the contact points that it's in contact. Oh, fuck. Hold on. Once again. Right there. That would have to be the reduction of your band. You couldn't use the full thing. So now you've got these smaller strips that you'd have to go all the way around. A lot more inspection. Just where it touches. Just where that touches. And you're talking maybe, I don't know, half an inch. That it's instead of the full giant roller. You're talking just a half an inch where it would do that, and then you'd have to inspect it. And would it really be pressing in? Being on a radius, would it really be pressing in? After you set it, after this gets set and you go to the next level up, the radius changes. You'd have to change this thinking on this too. It's just, I mean, I get it. I so get the theory on how this would work and how you need to improve this. But you'd have to change this head out. And then they would want to clump up on the head, as the head would be radius like that. These would want to bind up right there. As you fed it through there. It want to bind up, and it just, wow, this is it's a terrible. I get it for limited use. I can't get it for this radius. All right, I can't get it. No matter how you're rolling it, you're not staying that flat on this radius. So you'd have to change your shape of your sub to meet this radius. Steel, for example, it gets molded to that. It becomes, molded to that. This won't take the shape. It won't take the shape. Could you put it on there and somehow vacuum pack it? Yeah, you're going to get it nice and tight to the shape, but then you're going to create all this crap here. All right, all these inherent fractures, control joints. Yeah, I'll save that. Let's go. I want you to see his infrared.
The camera is we'll watch.
And then that's the end of the video.
Substrate, the heat from that goes through the material that we just laid down. And so with that, you can impart some sort of knowledge on how well you laid down that material. And so just looking at overlaps and gaps, for instance, if you have an overlap, now you're conducting that heat through twice the amount of material that you were before.
See that? And so if you come back too soon, you're now superheating or extra heating your materials, and they're not ready for that. So you've got to be wary of that. You just can't just do it all in one shot. And we saw them run that machine back and forth. That was the liner. There was no way it was not this machine. I mean, of course there is a way, but there was no way it was not this machine. Hell, I would probably argue that other machine would do better going back and forth if you could just figure out the ends and trim the ends off. It would probably do better than this system. I get why this system, though. It creates a band of tape that's just super strong. Every time this lays down a band, in theory, it's a perfect lay. It's a perfect layup, a perfect lay down onto the surface. It's got the consistency of whatever it is, 60,000 kips, 1,000 psi strain ability, tension ability. I get how that works, that it doesn't want to move. Then you have the glue interface with it as the composite action. I get that, but this is where I don't get.
And so it's going to have a different characteristic heating and cooling curve. Immediately it's going to show up as a cold spot. And on the flip side, if you have a gap, you're not going to see any heating and cooling. It's just going to be immediately cooling. And it's going to be
so this is kind of cool. He's going to use infrared, the flare device in a minute.
A much higher temperature because you're looking at just the preheated substrate itself. And so in fact, anything that happens between those, the old layer, the substrate and the new layer, we can see in the thermal data.
So remember how I said how you would each layer, how would you have to do a rebond connection to it? Well, he calls this the substrate, is what he's referencing. So this is the old one is put down. The last one becomes the substrate for the next one. So if you take this off and go get it autoclaved, it's now a different material that it's trying to bond to. Is that glue? Can that glue bond to there without, what's the shear value of it bonding to an autoclaved surface like that? Did it increase or decrease? Did it get more slippery or did it not? Therein lies the problem I have also, is that it was not tested at 5 inches. I can't find any testing where they've laid 5 inches in a tube, if you will, of this type of material, and they're using Boeing's product. I couldn't find anything like it. And then I just see defect after defect.
And so we did that.
So here's the head. Here's the beast, right? There's the carbon fiber toes and how it feeds through here, and there's the roller. Now you can see this is on a very unique shape, but if you look what I'm talking about, see the daylight right there? So this can feed carbon fiber, but not out to the edge, or it would have to be laying it down after the fact. After it rolls over, then it would be trailing and laying itself down by wrapping around after the fact. This is what it looks like over here. And these are all the different carbon fibers that they are integrating for this. How would you figure it out? You'd say, look, I think that one needs to be a little more flexible in the middle, not so much, and this and that. I think it would have, the glue is also what I need to work on this, where this thing can meter glue differently per the wraps. Right now they're just doing the toes, the different materials. How about metering the glue differently out of the heads? Each one having a little bit more glue based on like radiuses like this. It's just my thought. You know, I'm totally in for the carbon fiber idea, but in this case, on a radius, friggin' crazy.
That we've developed that system and put it on Isaac here at NASA Langley, and it's been used on several different
NASA Langley
projects for their quality control and process development cycle, and we've been really successful in that. And so just to get...
So this is perfect. These are your toes. See how it's on a slight bit of an arch? The inner curve and the outer curve. And this outer curve, if it was going that continuous that path, you could see they're not using the very ends. In this case, they're using it from here to here, as the contrast shows black. And so this heat, what heat's coming off of here? You see it's coming off. So it is heating the layer below. And we can see the pass below it. And look, there's the pass below that one. But this radius created this inside-outside curve deal, and it created a gap here, and this creates an overlap where this one doesn't get to sit down properly. And now looking at it coming directly out of the roller, it looks like, is this intentional? Steer induced overlapping gap. Steer. He does a lot of, this is testing, so they do a lot of intentional defects. This might be intentional. Let's see.
Give an idea of what that kind of data looks like. Now we have a image here. This is one single frame of the movie that we recorded with the IR camera. And now the overlaps and gaps are readily apparent in the course. The bright lines are going to be the actual gaps in between toes, and the dark lines are going to be the overlaps.
Okay, so just so you understand, because it's thicker, it's overlapped, it won't show as bright because you got two layers of the toe on top of each other. Here also, but interesting, you think it would be here too, and so it's already feathered off the temperature. So it's a real-time monitoring system that you have to keep your eye on, and I would say on the flare device. And they're going to get to the point where they're going to use computers and be able to stop this, like they're using computers to cut wood and things like that. Will they get to it with this? Boy, your infrared, your flare, your temperatures would have to be just... You'd have to calibrate it manually every time, because you'd have to say, okay, well, we're putting it on this product below. It's still at this temperature, but over on the other side, it's a different temperature. The room and this inner tube would have to be temperature controlled. So you would get the same gradation no matter what, all the way around the entire tube. And that's not going to happen, because when you get to the end of the tubes, that's going to off gas heat. It's going to release gradient heat off at the edges. In the middle, it's going to pile up heat. So, like right here, heat's out here and heat's here. It's going to pile it up. So you'd have to really, my gosh, this is just a mind fuck. You would just, yeah, you know, I can't, I'm trying to make this, so when you hear me stalling like this, that's my brain going like super fast mode, trying to figure out how you can make this work. And it would have to be automatically controlling temperature at the same time. And that would have to have a temperature feedback right here. So in the roller, it'd have to have temperature feedback saying, too hot, too much, stop the machine, slow the machine down. It all had to be integral. Even the temperature of the toe would have to be monitored to feed in here, and not last minute temperature controlled, but monitored as it feeds in. And maybe this gap is created because of the increased temperature from outside to inside, more heat being in the middle.
And so this is distinct enough and obvious enough that you can even build a computer vision system some sort of machine learning algorithm to automatically identify these defects and call them out at the end of a plot, which is something we've done as well.
So he says the computer system will automatically call them out at the end of the plot. And then what? What do? You don't take it off. You ruin the layer below. I mean, what can you do?
So anyway, once you get that,
Oh, yeah, I did see this part of the video. Okay, I remember this. I didn't watch all of this, guys, but I did see this part of video. This is very pretty. Look at that.
you can even do some more complex things with the data where you can construct a holistic model, a data reconstruction of your entire part, your entire ply, and you can see how your process parameters are exactly affecting your part quality. And so not only can you track a defect across from one course to the other, but you can also track defects through the plies. And so now if something's not in spec, or if something is a defect is in spec, in specifications for one ply, but it's lined up over 12 other defects below it, then all of a sudden that's out of spec. You can track it if you have sensitive enough data, and you can reconstruct it three-dimensional like this.
Okay, let me help you explain that a little bit. So what he's saying is, say you got 12 plies, and you find, and the computer says, hey, you got a defect right here at point X, X7, this location right here. So he's saying it's like, let's just do the whole screen there. 12 ply, let's just use 12. And so at the computer maps, it says, let me just put it over here in text. It says location X-77 B-66. That's a location. Okay, let's change that color. That's a location. And then it says this is on text. So text, it says, I'm going to say layer 2. Okay, let's just layer 2. And then it says text. Next, the computer says, you know what else we find on layer 2 at that location? We found on layer, the same defect repeats on layer 6, 7, 11, and 12. And ooh. Yeah, sorry guys. And yellow. So it says, it repeats, it says, here's your repeat. So now you've got it on layer 2, 6, 7, 11, and 12. And you've got 12 layers. So you have the balance of that. You have this defect located right here in this material. Let's say that points, that's location is right here. Is right there. And let's say you only have 12 plies. So you've got a significant weakness there. Now let's say it says it's X77, 66. And let's say it tracks it and says, it looks like this. Oops. It looks like this, that line. Now this is kind of spiral, so I actually can be a little more precise than that since I have a damn line here, since I do have their layout. I do have their layout, and it's kind of, look at when I, great. Watch when I pull this away. Great. Watch when I don't pull it away. It's kind of curved, so I can put that curve back in there a little bit. And there's our defect. Let's say it's right there. And that's just one. But let's say it's a whole bunch of them there, and it says defect here, defect here, defect here, defect here, and defect here. And let's say it doesn't follow it all the way out. They trim it so it doesn't matter on the ends anymore. Or it does matter, but it doesn't go to the ends. For some reason, at the ends, it just cleans itself up. So, but you're looking at think of breaking up a concrete jackhammer, and the stresses would be through here like that. And I'll stop at that one. So so you can see how you're getting cross-section and all types of issues going on here since they cross. These two, maybe I should have put another one closer. And putting these close, make this one to, say, a real-time monitoring system. Say, aha, we find that this area and this area and this area is a weak zone. And that might be the one that starts lighting up on an RTM, on a real-time monitoring system. But their system is able to, computer system, so he states this is only a year ago, show that. But then again, look at his overlap. See his computer system? Its modeling is not consistent unless the machine went there, jogged over, which it does not, and then jogged over and then jogged over. He's still making these blocks that are offset. These blocks are offset, so I know they're rotating in three-dimensional, but it would be more like this. But when they plot it like this, the machine resolution does this. But this would be more what we're looking at. As you can see, the bunching here, the bunching of the fibers here in this radius that they theoretically modeled would be, this one would be here. So you should get bunching there, and as he spirals the fingers out, if you will, it looks like that's wild. It gets wider there and tighter here. I definitely like to see what this piece really looks like if it exists, and that would be it to the left, I believe, but it's just a patch, if that's true. And you can see it doesn't match. There's the rolling the machine on it now. So he doesn't explain this. I made it this far in the video. Let me see.
Now, so that's all great. We've done that. You can add extra value and decision-making support to your project with this, but there's one issue. No matter what inspection system you use, you have to be able to qualify that inspection system, and you have to be able to have confidence in the inspection system's results. And the way you do that is through calibration. And so with
okay, I think I remember this calibration thing. Let me fast forward. I want to show you the. I might not have gone this far. Yeah. All right. So here's your course problems, your overlap, your gaps. All right. I want to show you what it looks like in real material. So these are the toes, and we're back to this one. Let's see.
A lot of times they'll happen in the middle of the course, and sometimes making those little adjustments are going to be hard with complex geometry.
Yeah, complex geometry. Yeah. Let's fast forward. We already dealt with that one. I talked to you about that one. I want to show. I think I saw. Might have. I've seen quite. Okay, this is one I wanted to find. So he's showing what just a little section of toe looks like, and the overlap on purpose, and it's the gap. So he purposely just cut it out to show the gap. And then over here he did an overlap, and I think it's going to zoom in on the next image, so you can see what an overlap looks like in real life. So you can imagine trying to inspect this. That would be easy to inspect. That one, really. So this is them attempting some jig idea to get it to work. And yeah, I remember this video now. I watched it quite a few days ago, but finally getting around to putting it to you now. This is what it looked like here. That's what it looks like, the overlap. There's the gap, one you just saw. This is the overlap. Look how small of an overlap, but look at the problems it creates. Remember the step down, like the tape I did on the roller, on the lathe? And I want to end this video now, I think seriously. I want to give a shout out to the supporters of the channel. Now you know that I'm back in the box, back in my YouTube jail. So we won't be seeing any new subscribers coming in really. We'll see people being unsubscribed. Not by me. I can't unsubscribe you. And then you'll be coming back in telling me that I thought I was subscribed to your channel. You are. YouTube will take out about 1,000 subscribers over the next few weeks. They've done it before. And then they will no longer push the content well, they're not pushing it now, but they'll push it even. I'm sorry. They'll send it to people that have no interest in this. People that are looking at the weirdest of things. They'll send it to them to suggest that they look at this. To make sure I don't do content, they have a high dollar monetization on my channel. So if you want to put a commercial on here, it costs you more than anybody else, $15, $16 per whatever it may be. And everyone else might be doing it at $7.50, which means it would be, quite interesting for a few advertisers to jump on board. But I've heard a few excuses. One of them was YouTube said, "Oh, your content is such high quality, we can charge more for your content because you're not doing a cursory, after looking at your channel, you don't do a cursory review of things, you deep dive. And so deep dive channels, we can charge more on advertisers for the people." I'm like, what? So, they're just blowing smoke. I think that's code for, we're going to teach you to be stupid. Do stupid videos if you want to make money on YouTube. You've got to do stupid, dumbed down videos with the thumbnails that show me with my mouth open going, "Oh, look, oh my gosh," and hold my mouth. I got to do those thumbnails. I don't want those type of people that need that type of thumbnail to, if I got to get you coming here like that, this is the deep dive stuff. So, it's interesting. I've been doing some research in psychology and things like that. I love psychology. And how much of this is me beating my head against the wall? Well, I'll tell you, I would have stopped beating my head against the wall if it wasn't for the sponsors of the channel. And now the cats especially, they got me pulling on my heartstrings now. So yeah, I'll keep going as long as that keeps, so. I'll keep doing it. And if something pops up that's of interest, I'll post it. I'll post on that. I think I want to show you something about asphalt buckling to change the subject for a second. I saw some street asphalt that was buckling. Looking at it, I did a video live, recording, and I state what I think I'm seeing, what this really is, and of course I nail it, because then I take it apart with my hands, the asphalt, and then I show you what's below it, and I'm like, there it is, exactly what I said. Hopefully the lighting was okay. I might have to adjust it because it was bright. It was hot that day, and the street buckled. So this is your toes right there. TOES, toes. Here are your toes here. Eeny, meeny, miny, mo. So on purpose, this is NASA doing this. So shout out again to the subsea engineers that are writing me on the side that I can't disclose who they are. They can disclose themselves. And if they do, they use anonymous names on the channel because they have to worry about their jobs. So really shout out to you guys for your support in the background there. Answering some technical questions I may have, guys. Shout out for them sharing, like content like this, saying, "Here, I think I found what you asked for." Because I asked them, "Can you find me something on X?" And they'll very fast. They'll find something for me, or email me, email me something, or show me a real world, one of their real vessels imagery, which I can't share with you, but at least I'll know what I'm looking at to share with you guys when we look at it. But this carbon fiber part, this is another level of engineering, just specifically with carbon fiber only, and that would be the specialty is the composite people. So this right now is being done by the Navy with small submersibles, not with the size vessel he used, which scale-wise we know it didn't work. 900 psi worked like a champ. Right, 900 psi, 74 minutes. Okay, then he killed the vessel and then scored it at 4,000. That's just craziness. So let's don't forget that. So it was never designed that 1/3 scale we saw. Now they hold out this rush and people like that. So keep an open mind that he did, 7 of these vessels, and he doesn't want to look like a failure. So he only publishes one and then does that. Maybe there's 7 of them that exist that we don't know about. Keep that in mind. And don't be so quick to not leave out that percentage that Rush was being crafty. And he did 7 of them. And this one was actually something that he tested that worked to 9,000 psi. I doubt it. I doubt it because he took down that one guy you guys know about, Stanley. into the vessel. Stanley, in his own words, paraphrasing, says that, oh, he let me take control of the vessel, and I could tell I was going deeper by the cracking sounds I heard in the vessel. That's paraphrasing him saying that. I'm like, well, if you know it was cracking apart and taking it deeper, why the hell would you keep going deeper? That was just craziness on Stanley's part. He was a crazy person to keep doing that. I'd be like, okay, I heard enough. As soon as I hear the first crack, I'm like, nope, don't trust this. This has not been tested enough. You shouldn't, under your Kaiser example, for example, we shouldn't be hearing this for the first time. We shouldn't be hearing it at all because it should have already been stabilized per his Kaiser effect. Per his Kaiser effect, yeah, that was a good long goodbye, wasn't it? Per his Kaiser effect, that fractures that they talk about in this video here, that they've already been load tested, the fractures already happened, he brought it back up, and then when he goes back down, it doesn't break anymore at that PSI. It can take that PSI again because it's stabilized. Those beyond that. But yeah, here we go. So much for the short goodbye. You guys got me doing it for real now. So this is not a planned goodbye, but this is one of my fake planned goodbyes. It's the real one. So think of that concrete sample I show you in my channel, where I show you that I can bolt it together from the underside and fix it. So let's just do, this is one piece of concrete, and this is the other piece of concrete. And if you remember, I showed you, if you look at the channel's image, I use this and I tie it across the back side. And when you load it here, and these are butted together at that point. These are butted together. Let me go ahead and butt them. So when you just butt them, they'll just break apart if you load it. They'll just fall apart. But I use this to hold it together. The back side of that all thread all, however you like to call it. I use that. So when you put a load here, it tries to put that in tension. It's the same thing as carbon fiber. He's got fractures here. They're here, but it can't go through, and it's picked up by the next band below, and the multiple, I don't know how many layers left. The multiple 400 layers left. And so it's picked up by the 400 layers above. So what you heard cracking were these layers. The problem is the cracks still exist. They're there. And these cracks under compression also want to push apart. They want to push apart also. And you don't get to push them. Well, that's a different one. I remember making one of these by mistake once before. This large one like that. And they want to push. Let me see if I can do it again. They want to push apart. Oh, wait a minute. But they're bonded here also, below the layer below, as he stated in the video, the substrate below. And if you move this fractured part against the substrate below, you're starting to weaken the next substrate. And it's so on and so on and so on per dive. I'm going to end the video with that, and I don't think I'm going to do any editing. All right, I'm going to post this one. So shout out to my people supporting the channel. This is a hard one to say. The two cats that I showed you, one of them I think died. I didn't live, but the white one lived. So you remember my opening video? Well, I'll put it in the opening of this video. The white one is very jumpy and bouncing around, and I'll show you that in a... maybe I'll grab it now and put it in the video to show you how happy she looks. But the other one I thought was going to live, and I actually thought the white one was going to die. I went and ran out and bought some food for her and everything else at the last minute. And then when I got back, the mother grabbed her and took her away, which is perfect. That would be Nancy. And I thought she was the one who was going to die. But it pulls at my heart a little bit, knowing that the one kitty died already. Doing the research though, it does. They do have a high death rate, but I'd hate to think I participated in that when I moved the trailer. All right, bye.